Now let's talk about recursion. Recursion is a function that calls itself. And you may have already been exposed to recursion in your daily life and just not recognized it. So, for example, some of my favorite example recursive processes is sealing an envelope. You moisten a flap, you fold it over, and you seal. You might have seen recursive definitions in a dictionary or another course. A compiler is a program that compiles. A teacher is one who teaches. These definitions aren't very useful per se, but they're recursive definitions. To understand recursion, you must first understand recursion. And lastly, recursive art. In this painting, we have Mona Lisa holding Mona Lisa infinitely. So let's talk a little bit more about recursion. So far, you might have been thinking iteratively in terms of loops. So for example, let's take the function of a factorial. So 5 exclamation point in math stands for 5 factorial, which is equal to 120 because it's composed of 5 times 4 times 3 times 2 times 1. So just to generalize this process, down at the bottom of the screen, we can see that n factorial is the number itself, n, times n minus 1 times n minus 2. Add all along until we hit 3 times 2 times 1. So one way to write that using a loop is to define a function factorial that uses an aggregator variable, in this case product equal to 1. And then for I in range 2 to n plus 1, it's multiplying product times I and storing that that product back into the product variable. This example code is from Python, where the range function begins with 2 and goes up by 1, up through but not including the endpoint n plus 1. So this will end up multiplying 2 times 3 times 4 all the way up to n. And then we return product from this function. So let's see if we can revise our iterative or loop-based solution into a recursive one. So in this case, we want to start off with a base case. Recursive functions always have a base case. So when n is less than or equal to 1, we're going to return 1. For those students of mathematics that are familiar with proofs, the idea of recursion is very similar to the idea of proof by induction. So you might notice a similarity here. So our base case is if n is less than or equal to 1, we're just simply returning 1. If it's -5, -100, 0, 1, we're returning 1. Now, the magic comes in the recursive case. So in this case, we're taking n and we're multiplying it by the factorial of n minus 1. So we're just figuring out what is happening at each step. It's almost like we're just figuring out what goes inside the body of the loop, right? This is really similar to what was happening in the loop on the previous page. N times the product. Well, the product is calculating the factorial, right? And so the computer is actually handling all the repetition for us. We don't actually need to type out that loop. So let's peel this back and see exactly how this works. So we're going to start with factorial of 5. And then, we're doing a manual walkthrough. We're going to take 5 times factorial of 4. Well, I don't know what factorial of 4 is, so then we do that. So we're waiting to calculate the 5 times bit until we've finished walking through factorial of 4. Factorial of 4 is 4 times factorial of 3. Times 2 times factorial of 1, and then we multiply it finally by 1. And so you might notice that this bears a striking similarity to the call stack that I mentioned in a prior video, functions calling functions. So the call stack is going to remember all of the individual calls to the factorial function. And what we're calculating is we're calculating factorial of 1, 2, 3, 4, and 5, and then we're doing a multiplication to pull them together. And then we start passing that value back up until we calculate our result. So another way to look at this is how I recommend walking through any of these examples by hand, is with a manual walkthrough table where you write down the call and what it returns. So first off, we call factorial of 5, and that returns 5 times factorial of 4. Now I don't know what factorial of 4 is yet, so I'll make a new entry in my manual walkthrough table where I call that, and I substitute in the parameters into the return statement, 4 times factorial of 3, and I keep going until I get to the bottom, and I finally have a concrete value with no function calls. This value of 1 is what I can then pass back up the chain. And so now I pass that data back in, and I calculate my factorial. So I know thinking recursively can be a paradigm shift, right? It's a new way of thinking for most people. But once you understand it and internalize it, it's actually less work for the human. It's less work for us to cognitively think through how to solve problems recursively. The computer does a little bit more work, but we do less work. A looped version, we do all the work. The computer's not doing it. It is slightly more efficient to implement things iteratively, but sometimes there's certain problems that lend themselves to recursion, and it doesn't make any sense to use a loop. There are some problems that it doesn't make sense to use recursion, and it only makes sense to use a loop. And so it's nice to use the appropriate tool for the job. So recursion is going to exploit the self-similarity of a problem to produce short and elegant code. We define, as a human programmer, we define the base case. We define whatever one step of that, what's happening in the middle, and then recursion does the rest of the problem for us. We do have to think through the process of the recursive and the base cases. So for example, here, this is another example of factorial that does not work, because if you'll notice in the recursive case, return factorial of n, we are not updating our n, we're not changing our n and transforming it towards our base case. So what you want to make sure, and this is true of while loops as well as recursion, you want to make sure that your loop variable is leading you towards your base case, or in the case of a while loop, your stopping condition. If you don't have that relationship, you're going to end up with what's called an infinite loop or infinite recursion. And so the challenge with recursion is that you have to keep in your mind both the whole piece that you're working on as well as the self-similarity of each of the subparts. And that can be kind of challenging, but you know what? It does occur in nature in a number of different ways. This is some Romanesco cabbage, cauliflower, excuse me. Here's the dragon's blood tree. Also, we can see the recursive nature. But you always want to have a base case. Imagine a human hand that was recursive, right? So we want to make sure that we always define our base case. So for example, here's an example where we don't have a base case. This is legal. This code will run. It will just never stop and return a result. There's no base case. So what I do and recommend that others do is that you write your base case first and then worry about the recursion. So it runs, but it doesn't help, right? So for example, there's a road sign over here that also is recursive, or other issues with not having a base case. So when we're designing a solution to a problem in recursion, we want to program the base case first, then find the self-similarity of the problem. What does each repetition have in common? Do one step in terms of n, and then delegate the rest to recursion. And typically that one step that you're doing in terms of n is defined by the parameter of the function. So let's just review. What's the difference between recursion and iteration or loops? Any recursive algorithm can be re-implemented as a loop instead, right? Any loop can be implemented as a recursion instead. So really, you should be able to write iterative and recursive versions to the same problem. And in fact, I may ask you to do that. Sometimes recursion is the clear and simpler way. So this is for data structures with a recursive structure. So for example, we saw tree pictures. There's a tree data structure. It really lends itself to recursion. You can do it. You can process a tree using a loop, but it is going to be a huge pain. It's going to be so much more work than using recursion. However, sometimes iteration is clear and simpler. So for example, if I'm working with a list data type, it's really going to lend itself to a loop, and that's going to be really intuitive and concise and succinct. And so what I urge you to consider is using the right appropriate tool for the job.